All right, welcome back everybody. So today we've got a proof for you and a neat little application. So the theorem says the following: let f of x be continuous on the closed interval ab. The integral from a to b of f of x dx is equal to the integral from a to b of f of a plus b minus x dx. Okay, so let's go ahead and prove this. And we're going to show that the right side is equal to the left side. And we're going to do this just by a little substitution. It actually won't be too bad. And so the substitution I want to make is I want to let u equal a plus b minus x. And so the derivative would be negative 1 dx, but I'm going to move the negative sign over. And so in this way we get the following. So let's take a look. So we get negative the integral. We're going to have some du here. And so let's write our new bounds. So our old x value here was a, so a goes in for x. Notice my new lower bound is b. And then my old upper bound was x equals b, so b goes in for x. And my new upper bound is a, and that will be f evaluated at u. But we know from Calc 1 that if we switch the order of integration, then we just end up negating the integral. So we have the integral from a to b of f of u du. But we also know from Calc 1 that the value of the integral does not depend on the name of the variable. So this would be the same value as this. And so that actually concludes the proof. It's a super short proof. And what I'd like to do now is look at an application of this. So let's apply this to an integration problem. So for example, let's say we've got the following. So let's say we've got the integral from pi over 6 to pi over 3. And let's say we've got 1 over 1 plus the square root of tangent of x dx. And so now we're going to apply our theorem. So remember that this is the same thing as the integral from pi over 6 to pi over 3 of 1 over 1 plus the square root of tangent of a plus b minus x. Well, a plus b is pi over 2 minus x. So here's the application of that theorem. And that's actually going to be pretty handy because that's cotangent. Remember, tangent of pi over 2 minus x is exactly cotangent of x. So we can call that the integral from pi over 6 to pi over 3 of 1 over 1 plus the square root of cotangent of x dx. And so we're going to multiply the top and the bottom by the square root of tangent over itself. So I'm essentially going to multiply, actually let's write that out. So yeah, we're going to multiply the top and the bottom by this quantity here, the square root of tangent of x over itself. So that's fine. I effectively just multiplied by 1. And so notice that this product will be the square root of tangent. This product will be the square root of tangent. And if you multiply carefully, these are reciprocals. This will be the square root of 1, which is 1. So I get the following. So you might look at this and say, well, why on earth do we want to do this? We're going to make a clever observation in a moment. So let's take note that these two, whatever value this is and whatever value this is, they're the same value, right? These two quantities are actually equal. So I'm going to say the following. So here's where I'm going to get a little tricky. So I'm going to say that the original, integral can be thought of as 1/2 of 2 of these. So that makes sense, right? So 1/2 of 2 is 1. So this is completely legal so far. But we made the observation earlier that this integral is identically equal to this integral. That means I can substitute this in for this. So that means I actually have the following. So this is 1/2 the integral from pi over 6 to pi over 3 of 1 over 1 plus the square root of tangent of x dx plus the integral from pi over 6 to pi over 3 of the square root of tangent of x over the square root of tangent of x plus 1. But the integral is additive, so I can combine these into a single integral, and that gives me the following. So now you can see why this is incredibly useful, because now I'm just integrating 1 in respect to x. But that's exactly the difference in the bounds. So that's 1/2 of pi over 3 minus pi over 6. But that's 1/2 of pi over 6. And that's pi over 12. That's the value of our integral. So cool theorem and really cool application.